Welcome viewers to ePathasala. The course today will be your topic on projections in GIS. A very important aspect, how you are going to project the data, how we are going to bring the data from real world to paper, sheet of paper. Some of the details in cartography we have seen that. This is meant for PG students of architecture. Please listen very carefully, and then it will be very convenient and easy for you to understand the various aspects of projection system. As we have seen in the last episode, the geographic coordinate system, or we otherwise call it as the GCS. What we will be doing here now is that what is a map and what is a globe. Of course, map, as all of you know, is representation of features on the surface on 2 dimension. A globe is your representation of the same in 3 dimension. In both the cases, we are bringing the features or objects on the earth surface to a scale. How do you bring that? So, what are the various advantages and disadvantages? Of course, obviously a map will be easy to handle because it is in 2 dimension, whereas a globe will be relatively difficult because you will have to carry that in a object as a slightly bigger one. Well, coming to the other aspects of that, as I was telling you in the last episode, GCS, Geographic Coordinate System. Please try to understand very clearly what exactly is GCS all about. What GCS will be defining is your location on the earth using a 3-dimensional spherical surface. See, that is very important. A 3-dimensional spherical surface is shown as a coordinate system x, y. Normally or invariably people misunderstand a GCS as a datum. It is not true. Datum is also a part of GCS. It is not a datum as such. It includes a unit of measure. As I was telling you, it could be latitude, longitude or x, y, a prime meridian and a datum. Say datum is part of GCS, and datum is based on say spheroid. Datum is nothing but a reference system. You use a datum as nothing but a reference system. How do you reference the data? A coordinate system is a reference system which represents the locations of geographic features from the imagery or an observations made from GPS or the data which is obtained from say survey, land survey. So, that is how you represent that. Normally, a feature is referenced by its latitude and longitude, because this is again an important thing. We will see that in detail now. Longitude and latitudes, as all of you know, is nothing but the angles measured from the center of the earth to the point it intersects on the globe part of the sphere. As I told you, all the aspects of the earth as such is considered as a spherical object rather than any other non-regular object, but still we call the earth as a spheroid or a geoid, literally meaning. For mathematical purposes, you cannot use a spheroid or a geoid. Hence, we presume that the earth is a spherical object, and we make measurements from the center of the earth, and the lines are joined or pointed towards the your spherical object from the center. So, as I told you, 0 to 359 or 360 degrees is divided in such a way the equator part of it, where in which it will come from 0 to 359 degrees, and all the projectiles are shot from the center of the earth till it reaches the surface of the spherical object. Already, as you are all already aware, longitudes are lines which are vertical in nature, which runs from north to south, and very importantly it runs on the x axis. General presumption is that lat long, latitude x, longitude y, this is what most of the people does. All of a sudden somebody asks you, you will say, yeah, latitudes are x and y. It is not true, it is not, latitudes are not x. On the x axis longitudes run, on the y axis latitudes run. Just visualize on your own, you will understand. You can see here from the drawing, from this central part of the earth or the center of the earth, lines are drawn here and measurements are made 0, 20, 40, 60. And as all of you know, this is your x axis and this will be your y axis. On the x axis longitudes run, on the y axis latitudes run. Lat long, it is y axis, not x y. Otherwise, to be precise, you say long lat, x comma y means long lat, then it will be perfect. On the x axis, you will be measuring the longitudinal values, on the y axis, you will be measuring the latitude values. The equator, the meridian or the prime meridian, and the equator will be your 0 0 on your east west, and the longitude will be your prime meridian from north south, and you have the graticules, and this is the divisions which are made. Now, what exactly is your projected coordinate system? The normal geographic coordinate system is 2-dimensional method of doing it. It is not projected, it is only coordinate system, as you do in a rectangular coordinate system, say 0 0 100 100. You just replace the 0 0 with latitude longitude, and the 100 is also obviously replaced with lot lang. So, we will have the projected coordinate system. What is that exactly? Is defined on a flat 2-dimensional surface, that is what is a projection. That is, you try to project the 3-dimensional aspect onto a 2-dimensional sheet of paper. Unlike a geographic coordinate system, it has the advantage of lengths, angles and areas which are constant across 2 dimensions. So, that is what is the projected coordinate system is all about. But this is not true when you are working with the geographic coordinate system, because normally this planar coordinate system or geographic coordinate system, unless it is projected, it is used for very small areas where there will not be any distortion or effect of your shape or area direction of your object. Of course, a projected coordinate system is always based on a geographic coordinate system that can use a spheroid or a sphere. As I just told you, earth is considered as a sphere, though it is a spheroid. In a projected coordinate system, the locations are identified by say x y coordinates on a grid with the origin at the center of the grid. As you have seen in the case of universal transversal Mercator, you use that. And each position has 2 values referencing to it, its center, with reference to the central location it is obtained. So, one specifies the horizontal position, whereas the other specifies the vertical position. The 2 values are otherwise called as x coordinate and the y coordinate. Please remember, x represent your longitude, y represent your latitude, and using that notation we will be getting the values. The coordinates of the origin will be x is equal to 0, y is equal to 0, when which nothing but the intersection of the equator and the prime meridian will start from there. And as you see this on any given network, that is a gridded network, these lines are normally equally spaced. The longitude or the latitudes will be equally spaced. So, one will be a vertical lines and the other one will be a horizontal lines, and with the x and y axis in control, we will be having the x axis values and the y values rather. And the units are also consistent and equally spaced across the full range of your x and y. Horizontal lines above the origin and vertical lines to the right of the origin have the positive value. So, if we just look at this simple drawing, so this is what is that. All the lines above this horizontal line to the right will be your positive. To the left of it, if you find out, x will be lesser than 0, that is x value will be your negative and y will be your positive. And similarly, in this case both x and y will be your negative, and in this case x will be greater than 0, that is your positive, and y will be your less than. So, this is your plus plus, that is your x value, and this will be plus minus, this will be minus minus, and this will be plus minus. So, this is how your values will be represented on it. So, all the 4 quadrants are represented here. What is a map projection? What is a map projection? How do you project the data? As I was telling you right from the beginning, projection is nothing but displaying the earth on 2-dimensional map, or that is on a sheet of paper. Whether you treat that earth as a sphere or a spheroid or a geoid, it is all nothing but transformation of 3-dimensional surface to create a flat 2-dimensional sheet of paper. And it is not all your say mathematical transformation, and that is in general called as a map projection. If you just look at this world or the globe as such, this is as you view the world from space, and the projection is centered at 72 degrees west and 23 degrees south, namely your say your UTM coordinates, eastern and northing. If you are looking from the sun, this is the way earth will appear on the particular area from or the noon time. So, what is a map projection? How does it give the relationship between the objects? So, it is nothing but the spatial relation between locations on earth and their relative locations on a flat map, and that is what is all projections are about. And very importantly, it is all mathematical calculations. There is nothing odd about that, it is all mathematical simple calculations. Of course, the most important aspect is that when I am transforming the data from 3 dimension to 2 dimension, it will result in some distortion, and that could be your scale part of it or your distance, or it could be your angle. Hence, we say that no map projection or no system can be 100% perfect with respect to those 3. Somewhere sometime the distortions will exist. How do you accept it? So, the distortion as I told you could be angles, areas, directions, shapes or distances. It could be one of them. So, each projection what they tend to do is that they try to have or they accept one or more projection and then create a projection system, and we maintain the others as such. So, it all depends on your projection system selection of that particular depends on what kind of application, what kind of study, and which has to be accepted, which has to be preserved rather, and which has to be distorted. As I told you very clearly, in reality a spheroid is not a developable solid, because in any form is something like take a ball, cut it into 2 and try to flatten that. Somewhere it has to represent it, it has to break. So, that is what is the problem with your projection system, the earth as such. So, it is not a developable solid, you cannot develop it as it. So, to transform the 3D data into 2D, we have the distortion which will be in the form of a shape, area, distance, direction and position. These are the 5 effects it will have. As distortion is not available, unavoidable rather, what we try to do is that we have to accept 1 or 2 distortion each of the projection and then create the projection as such. We say conformable projection, where in which we say where angles are preserved, that is the local shapes are preserved, other things are affected. Equal area or equivalent projection, areas are preserved rather, others are affected. Equidistance, where distance is preserved between 2 points, but others are distorted to extent. And then azimuthal projection, directions from a single point location to all other locations are preserved rather. These are the types of projections we have, the conformal, equal area, equidistant and azimuthal. Classification of projection, what are the basis for that? Projections are classed by the global characteristics it actually preserves. As I told you, it could be the area, it could be the distance, it could be the shape. Geometric approach to construction, either you are going to use the projection surface or the light source, from where you are going to put the light and what effect it will have. Obviously, isn't it, when you are just looking at, we are just trying to use the light, you have the globe and you put the light. You just try to move the globe, the light variation, there will be a lot of variation with respect to the shape of the object which is resultant from the light which will be projected on the earth surface. So, that is what is the light source, and the other one is your orientation of the object. Finally, the interface of projection surface to the earth. Where does it interface? How does it intervene with the surface? You can see very important aspects, the variables which are present in a map projection. What kind of that? As I was just telling you, with light as source, we say mnemonic projection, stereographic projection, orthographic projection. With projection surface as the base, plane or planar projection system, cylinder projection system or conical projection system. These are the various properties we get. With orientation or aspect as a criteria, it should be transverse Mercator or transverse projection, oblique projection or normal projection. So, these are the various types of projections which are available, and we will have to work on that particular aspect. As I was just telling you, we will have to work on say developable surfaces, which is developable, which is not developable. So, we say that or based on say development surface, namely cones, cylinders or planes, conical surface, a cylindrical surface or a planar surface. So, these are things which can be developed because as I just told you, transformation is made mathematically. So, geometric shapes we consider, it could be either a cone or a cylinder or a plane surface. As you see that developable, you find cylindrical or conical, how cones are used or cylinders are used. So, we just try to have the surface could be, as I just told you, it could be a cone or a cylinder, and this will be the cut line. So, when I just use the earth surface as it is, I use or cut the cylinder exactly here and then flip it open, or I cut this cone here and flip it open, and this will be the shape for your cone and this will be shape for your say cylinder. So, that is what is the excellent part of your geometrical shapes which are being used to represent the earth surface. You can see here cylinder, presume that the earth surface or the globe is within the cylinder. Just if I open it like this, what will happen? That is, the cylinder is there, the globe is there. When I open the cylinder, obviously the object also opens here. Of course, you have some constraints, but still that is the way normally we do. Similarly, in the case of a cone, we have the cone here and we put the earth inside and we flip it open. What will happen? How will it, what will be the effect? So, conical surface. The other method is taking a planar surface, I keep it on the earth surface and we try to project the object from beneath and see what will happen. So, that is the azimuthal. First one, we talk about the light as a source. If light is as a source, what will happen? What will be the type of methods or what will be the types of projections one can generate? Orthographic, one of the very pertinent one, which is a very important one, orthographic projection. The projection center is at infinity. You can see here from here. At infinity, it will be going, this will be the map surface. Stereographic projection, wherein which we have the projection center here, that is exactly opposite to the tangent point to the map surface. The mnemonic projection, where the center is considered the center of the ellipsoid, and this is where it starts, and from here you project the object here, the projection at the center of the ellipsoid. So, the orthographic projection, stereographic projection or mnemonic projection are based on the light source. And again, in the case of your projection systems, but as it is impossible to avoid the distortion, as I told you, conformable projection, equal area projection, equidistant projection, azimuthal projection. These are the three, where in first case shapes are preserved, second case areas are preserved, third case distance is preserved. In case of conformal projections, what it does is it retains the correct angular relation in transfer from globe to map, angles correct for small areas. Please remember that it is not that always you can have that, it will be the angles for small areas, it will be perfect. A small scale in any direction or point, but scale changes from point to point. So, that you have to remember, otherwise it will get affected. Parallels and meridians are always crossing at right angles, and large areas tend to look more like they do on the globe than is true for your other projections. Examples of this conformal projections here, Mercator projection and then Lambert conformal projection or conical projection. As I just told you, in the case of your conformal, this is what is your map part of it, a conformal projection, rectangle aspect. Here is something like a ellipsoid, equivalent projection. A Mercator projection, as I told you earlier, divided into zones, entire earth is divided into zones, and the zonal distance will be your 6 degrees. A conformal projection, Lambert conformal conical projection, as you can see that the cone is considered here, the earth is put inside and it is flipped open, and this is the way the earth will appear when you are using your conical projection. The other aspect is your equal area or equivalent area projection, where in which areas are preserved. We do not bother about the direction and the distance, areas are important. A map area of a given size, so for example, if I just take a 3 inches circle in diameter for example on the map, that will be presented or represented as same amount on the earth surface, irrespective of where the globe or map is located. That is why the equal area, you do not lose the area. The tendency is that generally, as I told you, the shape or the size or the area or the direction will be lost. Here in this case, area is retained as such. Maintaining equal area, what we require is that the scale changes in one direction should not be offset by scale changes in the other direction. So, that is very important. Here the right angle crossing of the meridians and parallels are often lost, whereas in the previous case it was retained, in this case it is lost, resulting in what distortion? Shape will be affected, but the area will be preserved. Equal area. Projection coordinate system, say you talk about your say map and the globe. You can see here the globe part of it, and the globe is projected from here and to a sheet of paper, that is your map. Kind of an elliptical object is being projected something like on a sheet of paper, a rectangular one or a square object, that is the way we does. So, 0 to 20 degrees is now projected here. So, area here of obviously you will find that A, B, C, D and E. As you just move away from the equator, that is this is the equator, considering this as the equator, area of A will be always greater than B, B will be greater than C, C will be greater than D and this will be greater than E, because as you see here, when you move away from the central part of the earth, the areas also gets affected. So, that is what is your co-projected coordinate system. So, in equivalent or equal area projection, as I told you, you can see how it is represented in this shape, in this format rather. When I try to compare the conformal or your equivalent, what will happen? In the case of your equivalent, it shows the true size and squish and stretch shapes, whereas in the case of your conformal, it preserves the true shapes and exaggerate the shape part with other details. So, you should take a decision which type of projection, which where I am going to use it. Of course, we will see when and all this at a later stage. This is how it will go. This is your equivalent and conformal projection. And we have the equidistant projection, the third type, where we depend on or we preserve the distance, because many times when you are trying to work with the data, you have to ascertain whether the distance is important or the shape is important or the area is important. In this context, we are going to depend on your distance part of it. Length of a straight line between 2 points always which is represented on the great circle will be there always uniform. Lines to measure from it is originate at only one place or 2 points. So, we use the plane surface. As this plane surface is touching or it is tangent to this particular globe surface, what will happen? So, we just try to have the earth grid and the features projected from sphere to a plane surface, that is from this 3 dimension to a 2 dimension here. So, this is what your planar projection. So, as you see here how it is projected, equidistant, and the types are equidistant and azimuthal. Lambert azimuthal equal area projection is this the way in which this is represented. You can see here how the areas are represented is your equidistant projection. So, this is nothing but as you see from the top of the earth surface, or as I just told you, you have the planar your plane and you have the earth here. So, both of them are when they are just intersecting, how does it appear, how you are going to see that. So, when I am seeing from the top of the earth surface, what are the areas which I can see here? This is the way you can see, because isn't it, you cannot see the entire area, you cannot see all the aspects, because you can see only top of the globe, you cannot see the other aspects. This is what your equidistant projection. Then azimuthal projection, as you know that there is always a true north and the your I was telling the magnetic north, there will be some variation. So, when you are just trying to draw a line between 2 points that which is depicting correctly, whether it could be the great circle root or it could be the azimuth. In the case of azimuth, this will be the angle between the starting point of a line and the north. So, this will be there, and this line can originate only at one particular point, it cannot originate anywhere. You just put at particular point and then you tell what will be this one. So, this will be the angle between the line and the north and then you try to project that. So, this is how it will be centered on rho 1. So, this is the central point and this is where the projection is taking place and this is how the earth will appear. You can see here each of them will be different. You can see this is your equidistant and this is your azimuthal projection. So, this will be the point of origin. When you compare a plane projection, planar projection, a Lambert azimuthal equal area from the globe, this is how it is represented. You can see the distortions you see here, it is getting distorted here and there. But of course, at the central point it will be perfect, whereas other places it will be incorrect. The very important aspect is your conical projection, what kind of method you are using. In the case of a conical projection, a globe is projected onto a cone which is then flattened. That is what I was telling you. This is what is your cone and the globe is present here or put inside and you rip it open or you open it and then flatten it. What is that? Is something like a cap, a Duan's cap, you know, Duan's cap, you just put it over the globe as such. Here the meridians are all straight lines, all the vertical lines are all straight here. Angle between all meridians is identical, throughout it maintains that, but unfortunately as you see here, this part here, this is getting narrower and narrower. So, the latitudes will get affected, the meridians are all maintained. That is what your conical projection surface. This is what your conical projection. You can see here how the cone is put into here and the light is put from here. As if you just presume this to be a transparent object, from the center of the earth if you are putting light, whatever you see here, whatever you see from this through the transparent object, those which are getting reflected onto your say the conical surface, that if you flatten, this is how it will appear. So, this is what is your conical projection, a very interesting aspect. You can see here, this is what I was trying to say, that in this case it is in the same method, one area and this is a different area. You can see here how the distortions are taking place, isn't it? See, these meridians are all okay, there is no issues about that, but the latitudes are all changing, the areas are changing, these are all parallel to one another, there is no issue about that. So, this is what is your equidistant conical projection. So, you maintain a particular distance, but you lose the distance with respect to your latitude. You can see here, see, as you just go away from this equator, the area is getting affected, the distance is maintained. Then you have a very interesting one, namely the cylindrical projection, the projection what we use it for in many cases. One of the aspects which it will maintain very perfectly, the cylinder. Globe is projected onto a cylinder which is then flattened, as in the case of your cone. Normally cylinder usually fit around equator, because that is where you can see this is what is the equator part, because this part only will be touching your cylinder, from there will be opening up. Meridians are again evenly spaced as a straight line, but the parallels varies depending upon the type of projection what we are going to use here. So, cylindrical projection, as you see here, again the light is put here and then when you are just trying to look at that, just presume this will be your transparent object, the light is reflected and whatever you see here, these are the objects are all shown here in this fashion. Relatively, when you consider conical, cylindrical projection is presumed to have a better quality and a good details are maintained properly. You can get this. In fact, Mercator projection is all more of a cylindrical projection. This is what is your Miller's cylindrical projection, a projection which is done or developed by Miller's. You see the entire earth surface. In fact, entire thing is shown in one, the entire globe as such is shown in a rectangular object. So, this is what about your general aspects. In the next episode, we will discuss about the light source as a location. Thank you.